Hello, my name is Mohsen Heydari, and today I'm presenting our recent paper on Agnostic PAC Learning of k-Juntas using polynomial regression. This is a joint work with Wojciech Spankowski and is being presented at AISTATS 2023. Let me start with L1 polynomial regression. Here the problem is to minimize the absolute loss instead of the usual 0-1 loss. The problem is expressed by this equation, where here yi and xi's are the samples. So yi's are typically the label, xi's are the feature, and we are seeking to find a polynomial p of degree at most k that best express yi based on the absolute loss. This problem has been studied extensively in the literature, and in 2008, Calite showed that if we take P star to be the best fitting polynomial in L1 regression, if we construct the predictor G by taking sign of P star minus some constant theta, then we're gonna get an agnostic PAC learner for a variety of classes. And these classes include k-Juntas, polynomially approximated functions, half spaces, and many more. And despite these significant results, the issue with L1 polynomial regression is that its running time is high. It's essentially quadratic in sample size n. On the other hand, we have L2 polynomial regression, where the objective is to minimize the square loss. It's essentially this equation. And here, the running time is lower. It's in fact linear in n. And based on this idea, we have several algorithms developed already. The low degree algorithm of lineal, the LS SVM, which is a variant of SVM with a square loss. But despite this low computational complexity, we don't have any agnostic PAC guarantees for this polynomial regression. We only have PAC bonds with distributional assumptions. And in this work, we in fact prove that L2 polynomial regression is agnostic PAC learner, at least for k-Junta class. So this resolves the problem, at least for k-Juntas. Let me start with the model. The model is the standard agnostic PAC. Here we have an unknown distribution D on the input-output alphabets. We are given n IID10 samples, and we have a hypothesis or concept class, which is a set of functions from x to y. There's a loss function, and we can define the generalized loss as the expectation of the loss. And let's say OPT is the minimum loss of the functions inside the class. Based on this definition, then we can say that an algorithm agnostically PAC learns a hypothesis class H if with high probability it finds a predictor G whose loss is close to the optimal plus some epsilon. And we want this to work regardless of what D is. So in order to understand the issue with the L2 polynomial regression, let me start with this argument. Let's say we are having n training samples, and let's P be the best k degree polynomial minimizing the square loss. Let's take y hat to be the sign of this P. Then let's compute its 0-1 loss. Its 0-1 loss is less than or equal to y minus p squared, and this is can be shown easily. If we take expectation, then we have the square loss here. We have this inequality. In this paper, our argument is that this is a loose bound and leads to weak PAC learning inequalities. Let's dive in further. For that, let's say f is the optimal predictor in a class, and suppose f is approximated by a polynomial of degree k. Let's call that p tilde, and let's say the square error is epsilon squared. Then we have this series of inequalities. The first one is borrowed from the previous slide. The second one is true essentially because p is assumed to be the optimal polynomial. So if I replace p with p tilde, the square loss is going to be increased. And the second inequality, or the third inequality, is coming from AMGM inequality and by adding and subtracting f here. And there's a factor 2 because of AMGM inequality. So here the second term, f minus p tilde, is the square error, which is epsilon square with a factor 2 sitting here. But the first term is going to be 8 times OPT. And then the factor 8 is coming because of this argument that for any function f with output being plus or minus 1, the indicator of y not equal to f equals to 1 over 4 y minus f squared. And because of that, we can see that minimizing the square loss leads to a weak learner with a loss which is 8 times OPT. Obviously, we want 1 times OPT to have an agnostic PAC. So in this paper, we focus on k-Junta, and then we show that we can have a tighter bound on the loss. A k-Junta is essentially a Boolean function h on d inputs, but whose output depends on at most k out of d inputs. So here's an example. Let's take h to be this function. So here obviously the output of this function only depends on x1 and x2. Therefore this function h is a 2-Junta in a 4 variable input system. VC dimension of k-Juntas has been studied. So the lower bound is 2 power k and the upper bound is 2 power k plus k log d. And learning and testing k-Juntas has been studied extensively in the literature. There are special cases of k-Juntas such as constant depth circuits, DNF formulas, decision trees, and there's a version of feature selection that relates the problem to the k-Junta because we are selecting k out of d features. Now, our first result in the paper states that the polynomial degree algorithm is in fact an agnostic PAC learner, and this is the excess loss. And you see the expression here which depends on the VC dimension of the k-Juntas. If we simplify this expression, then we are going to get the sample complexity of k-Juntas, which scales as k to power k and then log d, and then we have a runtime which is linear in n. So our results bank on a series of main lemmas. Our first contribution is to make a connection between PAC and then MMSE. The idea is that let's define y MMSE as the MMSE estimator of y from an observation z. So z can be anything. So in our case, z can be the vector of the features. Based on this definition, then we know that y MMSE is the conditional expectation. Then we develop this lemma, which states that if y takes values from plus minus 1, then for any predictor g, the generalization loss decomposes as this: 1/2 minus 1/2, the inner product between y MMSE and g. This inner product is nothing but the expectation of y MMSE and g of z. Moreover, the minimum loss is decomposed by this expression, where we have expectation of the absolute value of the conditional expectation. And based on these two, we prove that the optimal predictor is the sign of the MMSE estimation of y. Now, another main lemma is a tighter bound on the square loss and the 0-1 loss. The lemma states that for any real valued function h, if we take the sign of h, the probability of error is going to be upper bounded by OPTZ, which is the minimum error among all functions acting on z, plus u of this expression. U here is a polynomial, which is defined as follows. And this expression is essentially the square error between YMMSE and H of Z. As a corollary of this result, then we can characterize the optimal loss for k-Junta class, which is expressed by this expression, where here P star of J is the best polynomial, minimizing the square loss on the coordinate J for a given training set. Now, this was the L2 part of the paper. Now, we have another results for the Fourier-based algorithms. These algorithms have been studied from the low degree algorithm of lineal, which is essentially an efficient implementation of L2-Polynomial regression. They have been studied for PAC learning of AC0 functions. And what they do, they can help reducing the computational complexity to nkd power k. With L2, we have another factor here sitting next to k, which is larger than 1. But unfortunately, we have PAC bounds only for uniform distribution because these algorithms are banking on the uniform Boolean Fourier expansion. The Boolean Fourier expansion is defined as follows. So we know that any bounded function on the Boolean Q, here plus minus 1, so obviously here I'm using minus 1 instead of 0. Any such function G is uniquely decomposed as this expression, where S ranges over all subsets of the D coordinates. GS's are the Fourier coefficients. They are expressed by this equation. Chi-S's are nothing but monomials, which are basically product over J will belong to S of Xj. And this gives us the Fourier expansion. Here is an example. If we take the logical R, its Fourier expansion is as follows. And the issue with the Fourier expansion is that it is defined for uniform input distribution because of this summation. Although there are extensions to product probability distributions and also arbitrary distributions, we want to use this for agnostic settings. But surprisingly, in this work, we show that we just need to use the uniform Fourier. We don't need any other form of Fourier to achieve our results. And the idea is based on a simple adjustment to the Boolean Fourier. So the idea is as follows. Let's take dx to be an arbitrary input distribution. Let's f be an arbitrary function. Then we define fs as 1 over 2 power d summation over all x's, f of x, dx of x, and chi of x. So here you see that there's a d here, which wasn't in usual Boolean Fourier. If we take a closer look, we see that fs is essentially the Fourier coefficient of this function with the product of f and d. But interestingly, so note that in agnostic PAC, we don't know what d is, but we show that we can estimate the Fourier directly without knowing what d is. And before presenting that, let me just extend this notion to stochastic mappings. So here we have joint distribution on x and y, and then we can define the stochastic Fourier coefficients as follows. And then we can estimate this by just this summation. So 1 over 2d is the normalization factor. And then we can show that this expression converges to this alpha s for any distribution d. And based on that, then we make a connection to the 0-1 loss. And the connection is expressed as follows. If we have any predictor g, then its loss is decomposed by this expression, where gs are the uniform Boolean Fourier of g, alpha s were defined in the previous slide. Based on that, we get this stochastic Fourier algorithm. And these are the sample complexity and PAC learning guarantees. And here is a table of comparison of different algorithms, the brute force, the L1, L2, and all of that. And then you can see the computational complexity compared to the sample complexity. And these are our results. To conclusion, Here we prove the PAC learning bounds for L2 polynomial regression, and then we develop a stochastic Fourier with a series of innovations connecting AISE and PAC. With that, I finish this presentation. Thank you.